This problem is working with kinematics, rotational kinematics, so it should feel fairly familiar to you in terms of what we've done before way back at the beginning of the semester with constant acceleration. Because here, notice we have an angular acceleration that's constant, so that's alpha, of 4.0 radians per second squared. And so we have a wheel that has a diameter of 1 meter. And its initial angular velocity is 2, so initial angular velocity is omega. So omega naught is 2 radians per second. And then question A just asked for what is the angular velocity after 10 seconds? At t equals 10 seconds. So we can look through our three equations that we have for constant angular acceleration, and I'll just write them quickly down over here. We have theta equals theta naught plus omega naught t plus 1/2 alpha t squared. Omega equals omega naught plus alpha t, and omega squared equals omega naught squared plus 2 alpha delta theta, where that's just theta minus theta initial. And in this case, in terms of signs, because we've got angular acceleration increasing in the same direction as the velocity, it doesn't say one would be negative versus the other being positive, we can just use this second equation here and just drop everything in. It's pretty straightforward. Omega final equals omega naught plus alpha t. We've got everything, so omega final just equals 2 radians per second plus 4.0 radians per second squared times 10 seconds. Seconds, one of them goes away, and we get a final of 42 radians per second. Okay, that's pretty straightforward. B is through what angle does it rotate in the 10-second interval? So we want to know basically delta theta, or we can say theta naught equals 0. So now we want to know what theta is. Either way, we can set this up. You want to be careful though. Some people might want to use omega is equal to delta theta over delta t, and then substitute the values that you have in. But the problem is that this omega is not constant. And so while omega is equal to d theta dt at any instant, because this isn't constant, it's not clear. Would we use 42? Would we use 2? What value would we use? And so instead, we need to come back over here and either use this first equation or the second one, and either one will work. I'll just use the first equation. Theta is equal to theta naught plus omega t plus 1/2 alpha t squared. Notice that if alpha equals 0, then we can go back and use this equation where we just take our omega times our t, and that tells us what the angle is. Right, so if, then we can use omega equals delta theta over delta t, okay? But alpha is not equal to 0, so we've got to use one of these other equations. So putting our values in, this equals 0 plus 2 radians per second times 10 seconds plus 1/2 times 4 radians per second squared times 10 seconds now squared. Seconds all go away. This becomes 20 radians plus 200 radians, or 220 radians. Okay, part C, the tangential speed and acceleration of a point on the rim at the end of the 10-second interval. Okay, so at the end of the 10-second interval, we want to know the tangential speed. So if this is rotating in this direction, you would be looking at something like that, your v at the tangent, basically, which is our v. So v is equal to our omega, so v final, This v is increasing as we go along, but it's 1 meter. So we've got 1 meter times 42 radians per second. So v final equals 42 meters a second. Radians drops out when we don't need it anymore. It's sort of not a real unit. It's a reminder that we need to be in radians. And then tangential speed, and then acceleration of a point on the rim. So now the acceleration is interesting, right? Because the acceleration has two components. It's got the centripetal acceleration, and then it's got the acceleration associated with the tangential change in speed. So the speed that you're going around the circle is constantly increasing, so this A tangent is r alpha. That's the one we've just learned about. This AC, this centripetal acceleration, is the towards the center, the old thing that we had, which is still v squared over r. So in this case, it would be 42 meters per second squared over 1 meter. And this would be 1 meter times whatever our alpha was, which was 4 radians per second squared. Again, this becomes 4 meters per second squared off in that direction, but most of the acceleration is towards the center, this 42 squared. And 42 squared is 1,764 according to my calculator. Notice that one of the meters here cancels with one of the meters up above, so you still get meters per second squared. So we'll look at another problem that's very similar, just to see how this connects back to what we've worked with before. And that is, you've got a merry-go-round that's rotating at 2.5 radians per second. Okay, so that is now omega. It's 2.5 radians per second. And you're given the coefficient of static friction here. And the question is, how far can he stand without sliding? So if you're looking at a merry-go-round and you're looking at some point, some distance r from the middle, then even though it's going at a constant speed, a constant angular speed, so alpha is equal to 0, there's still an acceleration, right? And that's the centripetal acceleration. We saw it up above in the previous problem. So the centripetal acceleration is v squared over r, which if we substitute in v is equal to r omega, then of course this becomes r squared omega squared over r, or r times omega squared. And so the centripetal acceleration is going to be r times this 2.5 radians per second squared. And the question is, when does friction sort of let go and you can't stay on anymore? And so because friction is what's providing this force if you're standing there. So if we're kind of standing here, then friction between your feet and the merry-go-round are what keep you on the platform. So our friction force is going to point towards the center, friction, static friction. And so static friction is equal mass times acceleration. So it provides this acceleration. And the maximum value that we have is, of course, going to be given by mu s times the normal force normal, is equal to ma. And in this case, because assuming this is a level merry-go-round, that this is equal to mg. So we have mu s mg is equal to ma. So the acceleration, the maximum acceleration we can have then would be when we have mu s times g, or 0.5 times 9.8 meters per second squared, is equal to my maximum value of the acceleration that the friction can provide. And so the maximum value friction can provide is obviously half a g, 4.9 meters per second squared. And then we just substitute that right up here. And so we have A max is equal to R times 2.5 radians per second squared. This we put in now our 4.9 meters per second squared. Again, radians dropping out as we need it to, and we get a radius of 0.78 meters. Okay, so less than a meter is where it can stand. So it depends on how big this merry-go-round is. It doesn't say in this particular problem.